What's up, math scholars and math haters? This is Mr. W. If you have been keeping up with discrete math, then the last video you probably watched was on permutations. And you might be thinking, wait, combinations comes next in my textbook, doesn't it? It does. We are going to take a quick break from that and go over something called Pascal's triangle, which is started by this quick little array of numbers up here. This is not only one of my favorite things in math, but it also is going to lead into combinations, which will be a direct influence of binomial probability when we eventually get there. So the basic idea of Pascal's triangle is that we start at the very top with 1. And as we keep going down, we are going to start by just making sure we have 1s all the way down the sides.
And the way to generate the numbers in the middle of the triangle is a little trickier, but it's very simple once you see the pattern. Basically, for whatever hexagon is here, we're going to take the two numbers above it and add them. 1 plus 1 gives us 2. 1 plus 2 gives us 3. 3 plus 3 gives us 6. And so on and so on. Now, why is such a simple pattern being given so much attention in math, and why does it have to do with so many things? Well, we will keep going with that as we keep going in probability. I will go ahead and fill in the rest of this triangle, so you'll probably see this fast forward while I do that. It's generally easier, in my opinion, if you're being asked to fill out a big section of the triangle like this, to fill it out one diagonal at a time instead of one row at a time. So here's what we consider the first 10 rows of Pascal's triangle. I know that if you actually count the rows of hexagons, you'll see that there's 11, but we don't really consider this a row. We might think of it as row 0. But I want to point out two quick things in this triangle right now. First thing I want to point out is that it is symmetrical. You can see that we have just the natural numbers going down the second diagonal from the right and the second diagonal from the left. We have the triangle numbers in the third diagonal from either side, and so on. But essentially, if we know one number, we can go to the other side of the triangle and find the same number. 84, 84, 210, 210. The only exception for this are the numbers in the center. 1 at the very top, 2 in the middle of this row, 6 in the middle of this row, 20, 70, 252, and so on as we would keep going down. The second thing I want to point out is that we can find many different patterns, for instance, from circling or coloring in some of the numbers in this triangle. So I'm actually going to go ahead and demonstrate one of these patterns by coloring in every number in this triangle that is a multiple of 3. So 3, 3, and 6, 6, 15, 21, 15, 6, and 21. But we also have, in terms of looking for multiples of 3, this entire row and almost the entire row below it, because if any two multiples of 3 are added together, what you get is also going to be a multiple of 3. That's why 3 and 3 made 6, 6 and 15 made 21, and so on. And down here, this would essentially end up looking basically like another triangle in itself. So this is one of the other cool things we can see when we look at Pascal's triangle. And this will have some more implications for combinations and so on as we keep going in probability.